Thank you. So, hi everyone. So, my name is Olivier Grisel. I come from Paris in France. So, Jake Vanderplas should be around, but he's not there yet. He must be around. He'll join us. This afternoon, I'm gonna give some kind of complementary tutorial to Jake's tutorial this morning. On Scikit-learn, so in machine learning. And to be able to follow this tutorial, you will need to download the material from this URL. So it's on my GitHub account, so Grisel/parallel tutorial. So you can git clone it if you have Git. Otherwise, there is a download zip button on the page on the left-hand side, right-hand side. You will also need the Anaconda installer for Python, NumPy, SciPy, Scikit-learn, Matplotlib, and other stuff. So if you don't have Anaconda installed, and don't try to download it because it's gonna be too big. So I have a couple of USB keys here. So if you don't have it, please raise your hand. So yeah. So you need to install Anaconda. By default, I think the Anaconda installer will put the bin folder in the path, so that when you type IPython, it will use the IPython from Anaconda and not your system IPython. If you want to switch back to your system IPython at the end of the tutorial, you just have to delete the folder, the Anaconda folder, and it will not mess around with your Python installation in the system. Once you have downloaded the material from the tutorial, you can open a console terminal from your operating system. You need to cd into the folder that you unzipped or cloned, and into the /notebooks folder. From there, you can run the IPython command, IPython notebook, from inside that folder, and you will see the list of notebooks that we will need for the session today. So if you didn't put Anaconda as in the path, you can put the absolute path to the IPython command from the Anaconda distribution to type this command. Okay? So I'll leave you a moment to start the IPython notebook. So in the meantime, let me introduce myself. So I'm a software engineer at INRIA. So I'm doing, this is a research institute doing, my team is doing brain research. But myself, I'm working on the Scikit-learn project. And I'm helping the researcher in the team to implement the missing stuff or fix bugs. And I'm contributing to the open source project in general, and helping users on Stack Overflow and such. And I also review pull requests. Is there any setup problem to get the IPython notebook with the list of the notebooks set up? Yes? Jake? Can you please help him? Yeah. Here, him. Please raise your hand. Okay. So at the end of the tutorial, you will need to complete a survey for all the tutorials. So here is the URL. I will put it back at the end of the tutorial, but if I don't remember, please remind me to put the URL again for the survey at the end of the tutorial. So let's move on to the actual session for this afternoon. So when you launch IPython, you should see this page. And actually here, I'm running from the the solutions folder, and in your case you should be running from the notebooks folder, which is basically the same but with the solution stripped out of the notebooks. We can check that you have everything installed correctly. Let me clean up a bit stuff from here. No, you should be running the notebooks folder. So if you click on the first notebook, which is called tutorial setup, you can check that you have the requirement installed on your system. So from the notebook, I will just get rid of this to get some screen real estate. When you see an IPython notebook like this, you can click on the cells, and you can see that one cell is under a focus, and you can execute this cell by holding the Shift key and pressing Enter. Depending on the version of IPython that you're using, it might be Control Enter instead of Shift Enter. Hopefully. So when you hit Shift Enter, it will execute the current cell. You can see that there is a number here, and move on to the next cell below. So you can do that several times, and if you get import errors, then please ask Jake to help you, or check that you have installed Anaconda and that you are running the IPython version from Anaconda and not another version. You can also check which NumPy you are importing by calling the path attribute of the NumPy package, and you can check whether it's from the Anaconda folder or not, and the version this way too. We will also need a couple of datasets. So you can run this script, and it will download the 20 newsgroups dataset. Actually, we might not need it. It depends on how fast we go. But you can leave this command running in the background if you want, so that if we need it later, we will have it. In my case, it was very quick because it's already downloaded. And then it's stored in a subfolder here. Okay. So the outlook of this session, so it's meant to be an advanced version of the introduction to Scikit-learn. So hopefully you also already have some previous experience with NumPy, SciPy, and Scikit-learn. And we will go to see other aspects of machine learning with Python. And in particular, we will start with the first notebook, which will go through how to do predictive modeling. And in particularly, we will focus on how to do feature extraction from raw data, how to do to handle continuous and categorical variable in the same model, how to evaluate the model, how to deal with missing values, for instance, and try to make a predictive model and see how good it performs. Then we will focus specifically on how to pick up the best parameter for our model, and how to quantify exactly how the model is going, and how to diagnose the kind of errors it's doing to see what action we could take to fix and to make it work better. So this notebook here will focus on concepts such as overfitting, underfitting, how to plot learning curves, and to do grid search and parameter search in general. Then the third notebook here will introduce the parallel programming abilities of IPython.parallel, and that will make it possible to leverage multiple CPUs or multiple compute nodes on a cluster to distribute the computations that we might want to do with machine learning algorithms, especially when we want to do model selection that can be very CPU intensive. Finally, if we have time, we will also have a look at how to do feature extraction from text documents to tackle tasks such as text classification or text clustering or whatever. All right. So let's start with the first notebook, which is 01, an introduction to predictive modeling in Python. It's a bit big, so sometimes Firefox doesn't like it. Okay, sorry. Okay. So when you follow along, you should execute the cells as we go, because we might import variables and modules as we go, and we will need them later. So when you do data analysis in Python, we will use the traditional tools like matplotlib, numpy, and pandas. So here there are conventions to import those guys that are shared among the community. So for instance, myplotlib.pyplot, we import it as PLT, numpy we import it as NP, and pandas as PD. It's good to follow those conventions, because then you can share your notebooks with others, and they feel at home when they read your code. So the general workflow from this first session and for supervised machine learning in general is, first we start with a bunch of training documents in their original format. So for instance, if we want to build the predictive models that analyzes text, we will have, for instance, a bunch of text files on a hard drive, or a JSON flow from Twitter with the text of the tweet inside the JSON, or a database with a column of type varchar, for instance. So we need to have a way to collect those texts as Python strings, for instance, and to iterate over the collections. Machine learning can be applied to many kinds of data. So we could do a computer vision, and in this case we would have individual documents that are images or frames in the video. We could do speech recognition, and in that case we would have WAV files for speech, for voice recordings. We could do, for instance, product recommendation on a movie platform, for instance. And in that case, the original data that we would have would be the transaction logs of people hitting the play button on their movie player and recording the user interaction with the platform as the original data to try and predict how much a user is likely to like a movie in the future. So when we are trying to do predictive modeling, we want to predict something. And this something is a bunch of labels. So for each individual element, instance, object that we have in the training set, we will have a target label, a target variable that we are trying to predict. When we are doing supervised machine learning, we will need to feed those labels to the machine learning algorithm. So we will first need to collect labels, most of the time by manually annotating the individual rows in the database. Furthermore, we will, before being able to use the machine learning algorithm, we will need to convert the original data format into an intermediate representation, which we call feature vectors. And this part can be very domain specific and very important. There is no generic way to do that for all the domains. So during this session, we will introduce some strategies that might work very often, but depending on your domain of application, for instance, if you're doing computer vision or speech recognition, this layer will be very domain specific. So you have to read the literature to know what are the good tricks to apply at this point. So once you have a converted version of your original data and your labels, then you can run machine learning algorithm on that, and it will produce a model. And this model is something that summarizes all the relationships that you could extract from the training set between this and this. And it will summarize it in a way that is actionable, which means that in the future, if you collect new data, new items, you can apply the same transformation to extract the feature vectors for this new item, pass it to the model, and predict the most likely expected label for this new item. So for instance, if you're doing text classification to detect spams in comments on a web application, for instance, this will output a binary variable, is it spam or not, or maybe a confidence level for the prediction. All right, so this is the generic data flow. And today we are going to apply it to an old data set that has been used by statisticians for quite some time, which is a record of the passengers of the Titanic ship and whether or not they survived the event. So this data set is a CSV file. I've uploaded a copy of this data set on my Dropbox account. You can also find it on the Kaggle websites for machine learning competitions. And actually, it's a random subset of the original data set, so that it makes it possible to evaluate your model on this random subset. If you Google it, you can also find the complete data set somewhere else publicly. So here, to load the original data, we will use pandas. And in particular, there is this read CSV method that makes it very easy to parse a CSV data file. So here I don't pass any arguments except the pass to the data. But depending on the CSV variant that you have, you might want to change the separator character and so on. So let's execute this. Okay. Once you have this data object, you can call the head method, and you will see this kind of stuff. Let me change the resolution a bit. Okay. So head means that it will take the first 5 records and display them as a new data frame. So a data frame object it's kind of a 2-dimensional array, but the columns can have different types. This morning, Jake introduced how to do machine learning with NumPy data. In some cases, the original data is not structured and is not homogeneous. So you don't have numbers everywhere. For instance, if you have pixels, you can take directly the brightness of the pixels from an image. But when you query data from a database or for a CSV file, the individual features, the individual columns might have different types. And this is actually the case in this data. So here we have different columns. The first column is the ID identifier of a passenger. So it's just a count, an integer. Then we have a binary flag whether or not the passenger has survived. 0 for dead and 1 for survival. You have the class of the cabin of the passenger. So first class, second class, or third class, depending on the fare of the ticket. The name of the person, which is an arbitrary string. A categorical variable that says the gender of the person, the sex, so male or female. the age of the passenger, which is an integer, but it could be a continuous variable. So it's just the age. Whether or not there were sibling passenger on board of the ship. P-arch, I don't remember what it is. We can have a look later. Information on the tickets, the price, and the cabin number, and the city where the person embarked. So I think S is for Southampton, C for Cherbourg, and there is another location, I don't remember. So you can see that it's very, this data is not very clean because it's very heterogeneous, but pandas make it very easily to load this in memory and to manipulate it in Python so that we can do the feature extraction and clean the data and make it suitable to the machine learning. So we can first have a look at the count method on the data frame. And we see that we have 891 passengers. And for some of the columns, we don't have the record values for all the passengers. For instance, for the age information, 10% of the age information is actually missing from the data. So there is a NaN or something that is a placeholder that says that we don't have this information in the record. And for instance, for the cabin number, most of the cabin number, we don't have them. So it's good to take a look at the data just using the Pandas API to have a first look and see what's in there. So for machine learning algorithm, we will need, especially for Scikit-learn, we will need to convert this data as a NumPy array, because this is the Scikit-learn API. And if you take the values attribute of a data frame, you see that you get a NumPy array. However, you can see that the data type of that array is object. It means Python object. Because the data is heterogeneous, and because the different columns have different types and different meaning. And you can also have missing values like nans and strings and so on, all mixed up. So we cannot fit that. We cannot feed that NumPy array directly to Scikit-learn because of this heterogeneity. Furthermore, we will need to split the target variable, which is the second column here, from other variables that we will use as input data to make the prediction. And finally, there are columns that we don't care. For instance, the identifier of a passenger. There is no way we can generalize from this information because each passenger is unique. So they will have all different passengers IDs. So there is no structure in this type of information. So there is no relationship between this type of information and the target variable. So basically, this is the list of problems that we will need to solve to be able to make a model. So let's have a look at the target variable first. So when you have a data frame, all the columns have different names. I think you can have columns like this. So the list of columns there are marked as strings, and you can directly access the columns that have names that are compatible with the Python syntax, for instance, no white spaces, by using the dot notation. If you have names that are too weird, you can also use this notation, and you will get the same. So when I do data of survived like this or data.survive, I get the same view on the column, and each column has a data type. So the data type of the first column, which is an integer 64-bit encoding, and you can check that this column is an instance of a Python object, which is a series, an instance of the series class. A series class, you can think of it as a NumPy array of one dimension plus additional indexing information. But it's basically a one-dimensional NumPy array. If you look at the data frame itself, so the data object is an instance of the data frame class. It's a collection of columns, basically. You can think of it as a dictionary, a Python dictionary, where the keys are the column names and the values are the columns values directly. But it has many additional features to make it easy to deal with this data, like indexing, slicing, grouping, sorting, and so on. So for instance, we will group all the rows of our data using the values, the possible values of survived. So there are two possible ways to group the passenger that survived or not. And we can apply the count aggregation function on the result of this grouping and extract the values for the survived column this way. Here you can see that from this subset of the data, a bit more than 500 people died in the event, and 1/3 of the people survived the event. So you can actually compute the ratio by computing the mean of people who did not survive, and you can see that about 2/3 of the people died in the event. So this is really interesting because already we know that the target variable is not completely balanced. There are more people who died. So this means that if you do a model that always predicts the passenger will die, it already has 62% or 61% accuracy. So you can see that the chance level here is not 50-50. If you're not too dumb, you pick up the majority class, and you already have a 62% accuracy classifier. So you can also convert this column into a NumPy array by calling the values attribute on the column, and you can check the type of what you get is actually a NumPy array, and the data type of this series is also the data type of the NumPy array, and you can see that the encoding is 0 and 1 for survival or not. So we will start to train a first machine learning model on this data, and to make the problem easier, we will just focus on features from our original dataset that are already numerical. So if we have numerical attributes, we can feed them directly to machine learning classifiers from Scikit-learn because they all accept numerical descriptors. So here the columns that are numerical are the fare, the class, which is 1, 2, and 3, and the age. So actually the class, you could consider it as an ordinal categorical variable, but you can also treat it as a regular numerical variable. Because second class is between first one and third class. The price, the relationship with the price and the class number might not be linear, but we can treat it this way anyway. So to extract just those 3 columns from the original data, we can use the get method, or you can also use this notation, I think. Yeah. So you can use angle brackets and the list of column names that you want to select. And what you will get back as a result is another pandas data frame that is a subselection of those 3 columns. So here again, you can use the head method to see the preview of the first 5 records. So now that we have those features, we can have a look at the missing values, and we see again that the age columns has some missing values. So it means that some of the entries here might be a nan, not a number, which is a marker that says that the value is missing. So most machine learning algorithms in scikit-learn, they will refuse to work if they detect that there are missing values. So we will need to find ways to either remove the records that don't have that have missing values, or to find a way to replace the missing values by something else to make the machine learning algorithm work correctly. So a very common strategy to do that is to replace the records that have missing values by the median age, in this case, of the passengers. So to extract the median, we can take our data frame, only consider the rows that do not have a missing value, and compute the median on that. So if I do that, I see the median fare, the median class, which is 2, a second class, and the median age, which is 28. So now there is the FILNA method on the data frame, and I can feed it with the median values that I extracted on the non-missing value rows. And from this point, I can see that all my attributes have non-missing values. Okay. So we will see later, this is a bit, this is kind of cheating because we are considering the whole data set to find the median values to do the imputation. We see at the end that there are better ways, more principled ways to do that without introducing any modeling bias. So here again, so our data frame now is called imputed features because we did an imputation step. And now all the rows have actual values. And the missing values have been, the missing ages have been replaced by 28. Okay, so now that we have clean data, we can convert it into a NumPy array by calling the dot values attribute. And this is an homogeneous NumPy array with just numbers, numerical descriptors in them. So as soon as we have this, we can call machine learning tools from scikit-learn on that data. So the first step to build a classifier is to split the data between a training set and a test set, and we will keep the test set for the final evaluation of the classifier. And we will only consider the training part to actually build the model. So I'm using the train test split utility function from scikit-learn. You can see that it takes an arbitrary number of arguments as an input, and it will split each of those inputs into 2 outputs. And one will be for the training part, and the other one will be for the test part, and the size of the test part will be 20% here. And this process is a random process. It's shuffling the data before computing the split. So you can make it reproducible by fixing the random number generator seed here. If you want to get different splits, you can change this value and re-execute.
So that's the seed?
Yeah, this is the seed. Actually, you can pass...
0 is not a seed, right? 0 says you change it. I mean, if it's 0, it's actually using 0?
Yeah, it's the seed of the Mersenne twister. It's the Mersenne twister algorithm that is used to generate number generators, random numbers. So you can change it. Usually I like to put 42, but...
I guess my question is, if you use 0, it's actually going to use the seed 0?
Yeah, so the question is, if you put 0, it's going to use the seed 0. Yeah, I think so. Yeah, it's... the seed might be an offset to initialize the internal state of the pseudo number generator, to the random number generator. I don't know exactly the algorithm, but I think it's a bit shift or something at the beginning, and that's it. So now we have our train test split, and so we can see that the features array that we have extracted from the data frame here is now splitted into 2 different 2-dimensional NumPy arrays. So the first one is called features underscore train. It has the same number of columns as previously because it has the same number of features as previously. But you can see that out of the 800 something samples records in the CSV file, we have 20% that are in the test set and 80% in the training set. And we did the same for the target variable, which is survived or not. So it's a numpy array that is only one dimension. And you can actually check that the target test array has two possible values. So I take the unique values. So it's 0 and 1. I should have the same for the target train here. Because I have positive and negative examples in both my training set and my test set. It's actually good to do this kind of check because sometimes you might train on only positive examples and that you are not learning anything basically. But because of the shuffling, it made sure that there was both positive and negative examples on each side of the split. So one of the simplest machine learning algorithm that we can fit on this kind of data is logistic regression. So this morning we talked about support vector machines, and we saw that support vector machines, there are linear and nonlinear support vector machines. Logistic regression is very, very similar to linear support vector machines. It's a linear model. The kind of loss function that we optimize internally is different, but in principle, the performance that you get from a logistic regression model is very similar from a linear support vector machine. Furthermore, it's interesting because it's a probabilistic model. So by default, it will be able to output a confidence level in the prediction, which the support vector machines cannot do by default. You need to tweak stuff. So this is why I prefer this guy. Okay, so the output is a bit mixed, but when you fit a logistic regression model on the data, the fit method by default will return the object that has been updated. It's actually updating the object internally, but it returns it so that you can call fit and then predict or whatever, and you can chain the calls. This is why we return the object. So here you can see the string representation of the instance, and in the string representation of Scikit-learn in estimators, you can see all the hyperparameters that control the behavior of the learning algorithm. So here you see the C parameter, which is a way to control how much we regularize the model. So if you put a low value for C, it will have a stronger regularization, which means that the model will be constrained to have weights that are closer to 0. So it will be more constrained, whereas if you have a larger value of C, it will be free to put up arbitrary values on the coefficients, and it will make it possible to fit the noise of the data in an easier way, or to fit the data and the noise in an easier way. So there is a trade-off between taking all the data into account or to summarize it to simpler models. I think based on the normalization of the data, I'm not sure, but I think C equals 1 is the default values, and if your data is properly normalized, it's a reasonable default, and then you can divide by 10, multiply by 10 several times on each side. We will see that later when we talk about hyperparameter selection.
As an aside, what I was getting at with that 0 earlier is that if you provide none, then you will get that. That every time you run it, you actually get if you desire that every time you run it, you get a different value. You put none in for the reason.
Yeah, okay. Okay.
0 might do it.
Okay. So the question was the behavior of these random state guys. When you put 0, it's actually fixing the random number generator. If you put none here, it will, instead of using a new instance of a random number generator, it will use the NumPy default singleton. And it means that every time you call it, you change it, so it's not reproducible. You have arbitrary different stuff each time. Where you put none, you fix the outcome. But it's an arbitrary value as well. Okay. So my logistic regression model here has been fit on the data. And so once we have called fit on it, we can call predict to make some predictions on the new features from the test set. And we store the prediction in a new variable which is called target predicted. Once we have those predictions, we can actually have a look at what's in this array. So you have 0 and 1s. You can check the shape of the array. It's the same size as the number of oops. Here we ask the logistic regression model to make one prediction for each passenger in the test set. And you can see that we have as many predictions as we have passengers in the test set. So the predict method in scikit-learn, that might be a bit non-intuitive, but it expects two-dimensional arrays because it computes a batch of prediction at once, because it's most of the time it's more efficient to get rid of the Python overhead and to call the low-level libraries which are implemented in C or C++ or Python or whatever. So we compute the predictions all at once, and then we can compare the quality of the we can compute the quality of the prediction by comparing those predictions with the true values from our test set by using these functions, which is called accuracy score, which is from the scikit-learn metrics package. And here we can see that we have a 73% accuracy. So this function internally, it's very dumb. It's actually equivalent to computing the mean of the agreement of the true values with the predictions. So here you see we have the same thing. So we count the number of times our prediction is matching the true values, and we compute the mean, the average. So it's between 0 and 1. All right. Do you have any questions? Sorry.
I noticed you're doing the same thing that Jake had done in the previous class.
Yeah.
Import this accuracy score. Why aren't you just calling the score function off the classifier? Is there a difference between the two?
I think by default, for all classifiers in scikit-learn, the default score is the accuracy. So if I call, so this time I need to pass the X test and Y test. So it's a different API because it's gonna do the prediction and compute the score at once. Oops. It's not X, it's features. And target. So this core method here of the estimator itself is computing predict and then accuracy. Other questions? Okay. So now that we have a first model, we can try to have a deeper understanding on how it works. And in particular, since this is a linear model, we can introspect the coefficients, the weights that it attributed to each individual features of the input data. So here we can extract the column names as an array of strings. So we take the data frames, we take the columns attribute, and we call values to get an array. And here we have the column in the same order. The logistic regression object we call fit on the data, and once you call fit, you have additional attributes that are populated on the instance, and those attributes, they have the underscore suffix. This suffix is a marker that says that this was learned from the data. And you can see that in this case we get NumPy arrays with 2 dimensions, but in this case the first dimension is 1 because it's binary classifications, so we have 0 or 1 decision to take, so we can just use a single a one-dimensional array basically, and then we have 3 coefficients, so we could call Ravel for instance to get rid of this and get one-dimensional array directly. But we get those same three coefficients. So those coefficients can be interpreted as weights put on the individual features. So for instance, the first feature is very close to 0. The first coefficient is very close to 0, which means that the price, the fare of the ticket is not very important to make a good prediction for the model. The second attribute is minus 0.8, which means that the class number is very important, but negatively important, which means that the higher the class you have, the less likely you are to survive, which is logical because third-class passengers were closer to the level of the sea, and first-class passengers, they were on the upper deck next to the lifeboats. So it was much easier for them to get off their cabin and join the lifeboat. Because the crash happened during the night, so most passengers were actually in their cabins. And finally, you have the age, and it's again negatively correlated, negatively weighted, which means that younger passengers were more likely to survive as well. So here, you should not take those this absolute value into account, because it really depends on the scales of the features. And in this case, we didn't rescale the features. So actually, this is a bad thing to do. Most of the time, when you're calling a logistic regression and with heterogeneous features, you should scale them all to between 0 and 1, or to between to have a unit variance on all of them. But still, we can apply it directly and see that the classifier, even without scaling, is doing quite well with 73% accuracy. Actually, I think I did the scaling. I didn't change the predictive accuracy in this case. But the absolute values of the coefficient, they will be impacted. Yes? Okay, so the fair class, the question was the fair class, the fair feature should be correlated with the prediction. No, the fair and the class are correlated, so they should contribute in equal way, so they should be weighted similarly. I think this. And they get very different coefficients. In this case, this is precisely because we didn't scale the features. Because yeah, actually we can I will do let me try to do it like import scale. So I will cheat because I will compute the scale here. I will scale the features just before passing them to the model. And I will not compute the predictive accuracy because, or I can do it actually, scale, but here I will not scale the same way the train and the test, so I might introduce some errors, but it's just a quick and dirty way to check. So you can see that the accuracy hasn't changed much, it's actually decreased a bit. But we can check the coefficient values now. And now you can see that the fair is more important. Still, the class is still more weighted because maybe it has less noise than the fair because people were not paying the same for the same cabin, for instance. So maybe the fair has more noise. But you can see that the absolute values of the coefficients are very much related to the scales of the features, whereas the predictive accuracy of the model, not much. So if you're interested in introspecting and understanding stuff, you might need to scale and be careful about this.
Those are saying as the fare goes up, your probability of surviving also goes up.
Yeah.
And as your class goes up, your probability goes down, and that makes sense because 3 is worse than 1. So I think that.
Yeah. So the comment was the fare is positively weighted because when you pay a higher price, you have a cabin that is upper next to the lifeboats, whereas when you have a lower class, it's negatively higher class. It's negatively correlated because you are you are not in the same. Yeah, it's opposite direction. Okay. I just want to restore everything in the same as it used to be to make sure that I'm not changing the outcome for later. Okay. So here I have the absolute values of the coefficients. I can also use matplotlib, the PLT object, to do a bar plot of the coefficients. And you can see a visual representation of the weights. So here again, I recomputed the coefficients without the scaling, so you can see that the fair is ignored because it's highly correlated with the class actually, and the model picked up the class because the features were not scaled. Okay. Up to this point, we evaluated the model only with respect to accuracy, so the number of times we did the rate of good predictions. There are other ways to compute metrics to evaluate the quality of the model, and one way is to instead of considering hard class assignments in the target variable, we can compute the confidence of the predictions for the two possible values, the two possible outcomes, which is not survived and survived. And so here you can see that we get two-dimensional arrays of probabilities, and so each row in this array will sum to 1. So those as complementary values. So you could actually only consider the second column to get the probabilities of survival according to the model. Okay, so this is NumPy's array slicing. So once you have soft probabilities of the prediction, you can compute other metrics such as the ROC curve, and the ROC curve, we can actually plot it. So the ROC curve is basically I'm plotting it. A curve that considers different level of threshold to make to compute the predictions. So it will threshold those predictions as different level. And for each value of this threshold, it will compute the false positive rate and the true positive rate. So this is called also called the sensitivity. So it depends on whether you are weighting too much to make a true positive error or a true negative error, false negative or a false positive kind of errors. So depending on the applications, maybe it's more important to classify, for instance, something as spam, whether it's spam or not. Whereas classing an important email as spam might be a big issue. So by changing those, you can plot this curve here and consider the surface under the curve here, the area under the curve. And a good model will have a curve that is very close to those two axes here, on the left and on the upside. And a model that is predicting at random will be close to the diagonal. So here you can see that the area under the ROC curve is 76%. So this is interesting. It happens to be close to the accuracy level, but in general it doesn't need to be so. And in particular, if you have a very imbalanced data set with, for instance, very few positive examples and a lot of negative examples, it will be very easy to have a good accuracy, but much harder to get a good ROC score. Because if you have very few positive examples, you can always predict negative and you will have a good classifier. Whereas the ROC curve, as it considers all the possible trade-offs, it will penalize models that are not smart enough. So we can also compute the confusion metrics as Jake demonstrated this morning. So to recap the confusion matrix, we'll take the true outcomes as the rows and the predicted outcomes as the columns. And for a good model, you should have high values on the diagonal, and the entries that are off diagonals are errors. So here it predicted that 98 of the 100 people who did not survive has not survived. So those are good predictions for people who did not survive. And it predicted 33 people have survived. But also out of the people who survived, it predicted 36 times that the people were dead. So you can see that there is an imbalance between the kind of errors it makes. It's not very symmetric. We can also display the classification report, which is from the Scikit-learn metric as well. And you can pass in target names to make it easier to read the report. And this report will compute precision, recall, and F1 score. So precision, for instance, for the positive class is out of all the predictions that we made as positive are how much were actually true positives. And recall is out of all the stuff that we should have predicted as positive, how much we did picked up. So you can see that the model is as a trouble as we can see that from the confusion matrix is matching actually. And finally, the F1 score is some kind of in between the precision and the recall. It's an harmonic mean. So it will penalize models that have either a bad precision or either a bad recall. Okay, so both the F1 score and the ROC area score are good at quantifying the accuracy of a model on a problem that has imbalanced target variables. If you know that your target variables are well balanced, for instance, when we are predicting digits this morning, we have as many examples of each digit, then in that case you can use the accuracy score without any problem. Okay, any questions on these metrics stuff? No. So now to compute those scores, we did a single train test split, and we fixed it with the random number seed. We can try to change that that seed to compute different kind of splits, and for each split, we will fit a new model using logistic regression fit on the train part, and we will score it on the test part. And you can see that we get the 73% accuracy as previously because we used the same seed here. But if I change it to 1, I get 77%. And if I do it again, I get 67 and 66. So you can see that this value actually was a lot of chance to get such a high value here. There is a lot of variance in our estimation of the score of the model. So it's very sensitive to the random split, and this is because we don't have much data in this data set. If we had a lot more data, like millions of points, then we would not need to do that many train test splits. So to automate this way of trying different test splits, what we can do is a procedure which is called cross-validation. And in Scikit-learn, we have a tool that does this loop of computing different train test split, fitting a model on the train part and scoring it on the test part, and then recording the score in an array for each possible values. So this cross-val score here takes as an argument the model that we want to evaluate. So it's a model that is not fit, it's just the model and the hyperparameters. Takes the input data and the target variable to predict, and also takes a CV object. CV means cross-validation. And by default, you can pass integers, or you can pass arbitrary object to split the data. So if you pass an integer, it will do k-fold cross-validation, and the number k is the integer that you pass. So if I pass 5, it will split the data into 5 chunks. it will take 4 chunks for the training set and the last chunk for the test set, and it will do that 5 different times with the 5 chunk each time being used as a test set. So the test set is moving each time. And each time we quantify the quality of the model on the test chunk, and we record it as an array. So once we have those possible scores, we can compute the minimum value, the average value, and the maximum score that we get across those 5 possible folds. And you can see that on average the model is around 70% accuracy, but it's moving quite a lot. You can also use the cross-val score method to compute other metrics. So by default, it's using the score method of the model, which is the accuracy of the model. But you can use the ROC AUC score. And in that case, it's slightly higher on average, but it's moving even more. So the variance is even bigger, but it's slightly higher. So as an exercise, you can try to replicate this in a new cell and change and compute cross-validation metrics for different kind of metrics on this same data, on the feature arrays, using the logistic regression model. If you want, you can try on other scikit-learn models if you remember from this morning. And you can also change the value of the number of cross-validation folds between 3 and 10, for instance, and see the impact on the mean score and on the processing time. So I leave you a couple of minutes to try this. So you need to execute all the cells from the above if you haven't done so up until that point. no problem. So, okay. So I'll show the solution to this exercise. So first, we can compute the F1 score instead of the accuracy by passing the scoring argument here. And so you can see that the F1 score is much lower because the recall was bad, I think. The precision was good, but the recall was bad, and the F1 score is penalizing the model because of that. So it's around 0.5, 0.52. We can change to other values like Rocky, you see, I think we already did. We can do the precision, for instance. The precision is quite good, and the recall should be worse. Yeah, the recall is bad. Okay, so the other question was changing the values of the cross-validation, the number of fold of cross-validation. So you can see that here I put the time magic, which is a cell magic from IPython, and will time the execution of this cell. So you get the output here using a print statement. I did a print here, and you also have another output, which is the timing information for the execution of that cell. So you can see with CV equals 3, I can do another print statement that actually print the scores array. So with CV equals 3, I get 3 values. And okay, those are the values. If I do that again with CV equals 5, you can see that the training time went from 8 milliseconds to 70 milliseconds because it had to fit 5 models to get the 5 scores instead of 3. So you can see that it's roughly linearly increasing with the number of models. We can check that with 10. I'll do a print. So now I have 10 scores, and you can see that this is actually almost 3 times as much as 3, because 3 by 3 equals 10. Okay, so for the min and max values, you can also compare that the mean value is almost the same, it hasn't changed much, but the min and max values, when you try harder, you can see that they are spreading because you have higher likelihood to get extreme values by iterating several times. So if you compute the mean value with 10 folds, you have a higher likelihood of getting an accurate mean values for the cross-validation because the standard error of your estimate is reducing. Also, actually, this is not reflected here, but it can happen that with CV equals 10, that you would get higher mean accuracy than with CV equals 3, even if you did it many times with random shuffling of the data. Do you have any intuition if you observe this? This is not the case here, but why would the mean score of cross-validation would be higher with CV equals 10 than with CV equals 5 or 3, for instance? Yeah. So the answer was with CV equals 10, the training set will be bigger than with CV equals 3, because when you do CV equals 3, you divide it into 3 folds, and you train on 2/3. With CV equals 10, you train each individual models with 90% of the data. And in many cases, when you have more data, your model is more accurate. Otherwise, it means that your model is not very interesting. So here, it seems that if the model is not being able to improve, it's not doing worse, but it's not being able to improve, it means that either it's too biased because it's too constrained, it cannot benefit from having additional data, or it means that you have too much noise in your data, and whatever model you try, you will never be able to do better. So we'll discuss about that later. Okay, so now this was the first iteration of predictive modeling. And we used only numerical features from the original data because it was easy to do so. Now we can try to build better models by having additional richness in our data by extracting features from the other columns of the CSV file. So the columns that we will consider now are categorical variables. So categorical variables are variables that have fixed numbers of possible outcomes. For instance, the sex columns can either be male or female. And when you have a categorical variable like this, you can use pandas to extract what we call dummy variables. So it means that it will explode this column into as many different columns as you have possible values for this variable, and it will put binary flags for the presence or absence of this possible target value, not target, feature value. So for instance, let me put the data not head of 5. Okay. I want a data frame that is restricted to this column. So this was the original representation of the sex column in the CSV file. When I call get dummies on this, it will create a new data frame with the two columns exploded, and the values are in the column names now. So this is very nice because then we have a numerical representation of the categorical variable. And this is actually a not stupid numerical representation, because we could also have used another representation, which is to give possible different integers for different values. For instance, 0 for male and 1 for female. Actually, in this case, as we have two outcomes, it's equivalent. But for this guy here, if we explode it, we have 3 columns. So for Cherbourg, Southampton, and I don't remember the last location. But here, if we had decided to give Cherbourg 0, Q equals 1, and Southampton equals 2, and give that numerical features to our model, it will have implicitly expected that C is far away from S, and Q is closer to S than than S is close to C, because you give it a numerical grade between 0 and 2, for instance. When you do that, this binary encoding, it cannot compare the different values of embarked between one another. It only knows whether the person has embarked at Cherbourg or not. So it's a better way to encode the features, especially for models such as logistic regression, which whenever it sees a numerical feature, will take the scale into account. Here you can see they are all on the same scale, between 0 and 1. Okay, so now that we have found this way of dealing with categorical variables, what we can do is use pandas concat function to concatenate different data frames together into a new data frame. And what is important is to use axis equal 1, because otherwise the concat method will stack the data frame below one another, whereas when you use axis equals 1, it will stack the data frames as new columns. So here we extract the numerical columns that we used previously, and we extract dummy variables for the sex and embarked columns. And we display the data frame that we obtain. So you have numerical features here and categorical variables that have been one-hot encoded here. Yeah. So the question is, for the cities, why is it not better to use 0, 1, 2 for C, Q, and S? And the reason is that if I use 0 for C and 2 for S, the distance between C and S will be 2, and the distance between Q and S will be 1. So it will implicitly make induce the model into thinking that C and S are far away, whereas there is no such relationship. People who embarked in a Cherbourg is independent, is just not the same as being embarked in Southampton, but there is no relationship between those three cities. So this is why we use this encoding. Actually, in other models, for instance, random forest in Scikit-learn, it's not that important. You could have used integer variables for different categories, and the random forest would have been able to move around this restriction if you have enough data. But for most scikit-learn models, it's very important to deal with categorical variables by extracting dummy variables this way. Furthermore, you can see that the two sex columns, male and female, they are complementary of one another. So actually, you could just drop the male or female column, and you will not lose any information because they are completely anti-correlated. So we can do that by calling reachFeater.drop sex male equals 1. Once, I don't remember 1, but it's important to put. Why there we need to put 1 here, but if you don't, it doesn't do what we want. So, and here we have the same information, but we got rid of one dimension that was redundant. So there are a couple of questions. So first.
Yeah. By the same token, I mean, I see why you took away male. How come we don't have to do one for the embark? I mean, aren't those complementary?
Yeah. So the question is, why don't we get rid of Southampton, for instance? It's or Cherbourg. Actually, yeah, it's redundant, but it might make it easier for the model to have those three because they're not exactly anti-correlated. It's just an intuition, but it depends on the model that you're using afterwards.
So I mean, a lot of regressions. You know, I mean, even if it's close.
Yeah. So the problem is that because we are using a linear model, some models they like correlation, some models they don't like it, and would not be able to reconstruct the missing stuff. It depends on the kind of penalty that you put on the coefficients and so on. So you my best answer would be to try both and see if it improves the cross-validation score. Yes?
If we don't know the sex information from some people, would it be better to keep the two columns separate and have 0, 0?
Yeah.
The one to know?
So the question was, if we don't know the sex for some people, if we have missing values, would it be better to use the two columns, to keep the two columns and have 0, 0 on each side? That would be a possibility, but it might be better to, instead of putting 0, 0, to put the majority also. So same again, I don't know. It depends. It might be better to input the median or the most frequent value. Or you could also do this and have an additional column for a marker that says this value is missing. And for non-linear model, it would be able to leverage this if there is a statistical structure, a statistical correlation between missing values and the target variables. That might be important to increase the predictive accuracy of the model, even for a linear model, actually. If the missing values are not random, but they happen to be correlated with the target variable, it might be interesting to put an additional column to flag the samples that have a missing age or a missing sex value, for instance. Actually, we don't implement this in Scikit-learn, and we should. Okay. So again, now that we have our numerical description, we still have this missing values problem. So we apply the same strategies as we did before. So here we call the median method on the rows that don't have a missing value to compute the medians of all the passengers, and we call fillNA on the median, and we input them for the missing age. You have a question? Yeah, so the question was, does drop NA drop the entire row? And yes, and this might be an issue because sometimes you have a missing value on the age, and not missing value on another attribute, and you would drop this value to compute the median for other missing values in the same column. So you would lose information to estimate this. Actually, in this case, we just have the age column that has missing values, so it's easier to put it this way to drop the, because we just have one column that is problematic. The other columns, they all are full. Whatever. The cabin column, we don't use it yet. In this example. Actually, I never used the cabin column in the whole notebook. But yeah, you could do a better way of computing doing the feature imputation by just doing different imputation for different variables and dropping just the rows for a given variable, the rows that have missing values, compute the median there, and then do the imputation. Anyway, in our case, it's not a problem. So now we have the new rich features final data frame that has the categorical values, the imputation, and the numerical values. So we can train again a logistic regression model and do a cross-validation of the accuracy using fivefold. And you can see that this time we can reach 79% accuracy actually. We can change the value of the regularizer, c equals 1 here, and see if it improves. So I can try to increase the regularization by decreasing c. And it's actually improving a bit, but it might be just a random noise because it's very close. But if I put a too strong regularization, you can see that the model is, the accuracy of the model is decreasing. And if I do very strong regularization, the model will be 0, 0 everywhere. Just there will be a weight, and actually it will predict the majority class. So it should go up to predicting the majority class. So it should reach the 2/3 stuff that we've seen previously. So by changing the regularizer value, I can tune it and get almost 79% accuracy on average. Okay. So you can see that by adding new features here, we were able to increase the quality of the model because there were some information that was not captured in the existing numerical features. So for instance, apparently, actually this is the question later, but apparently at least some of those features are good predictors for the target variable. So now there is another exercise which I did partially actually. The first element was to change the value of C and what impact does it has on the score. So you can skip this. And the second part of the exercise is to fit. Oops, sorry, I shouldn't show the solution. Is to fit a new logistic regression object on the whole training set, on the whole feature set that we extracted, so rich features final here, and to plot the weights of the coefficients, and see which feature is important or not to the new logistic regression model on those features. So let's do it. A couple of minutes. Okay, I'll have a look at the solution because then we will be too late. Okay, so here we fit the logistic regression model on the whole data set, so rich features final target. And we extract the column names again, and we put an x-axis for the bar graph, which is just a bunch of ticks, and we need as many ticks as we have features. And on the y-axis for the bar graph, we will use the coefficients obtained by the new logistic regression model. And I can adjust the tick locations. I can put additional labels on the ticks using this matplotlib trickery to have a look at the meaning of each column. So here you can see that again the fur is not very important because it's most likely encoded by the P class because they are highly correlated and not scaled properly. And the P class is negatively correlated as previously. The age is slightly negatively correlated, so younger people have a higher chance of surviving. And you can see that being a female helps a lot in surviving the Titanic. Most likely because they say women and children have the priority. And you can see also that apparently the embarking at Cherbourg, or I think it's Queenstown or something, gave you a higher chance of surviving, but as we didn't scale those features, I'm not really sure about we can interpret anything about this. All right, so we could do this again with scaling again and see how it impacts. And now we get the opposite for those guys. So I think it's maybe people who embarked at Southampton were closer to the lifeboats. It's possible, but all right. So now you can get what the linear model is thinking, how it's computing its prediction, and you can have an interpretation. But again, those absolute values here, they don't really mean anything because in the real life, whether people or not would survive was not determined by a linear model. So the linear classification assumption is false, so the actual values are false. You can just have a look at the sign and maybe relative importances. So because of this, the linear assumption might be false. We might want to relax it and to try more complex models, for instance, ensembles of randomized trees. So in Scikit-learn, we implement a random forest. And yes, you have a question? Okay. So the coefficients, the question is the coefficients that we get are for logistic regression. And logistic regression is a parametric model, so you could, in theory, extract p-values to have an idea of whether it's a bound on the uncertainty of the coefficients. Actually, in Scikit-learn, it's a library that is focused on making good prediction and not really on parametric modeling, understanding whether or not the parametric assumptions were met. And the library that we use to implement the logistic regression in Scikit-learn is liblinear, which is a C++ library which is tuned for efficiency but doesn't compute the p-values. So it might be possible to re-implement that on top of liblinear, but we didn't do it. If you really need this, if you are more like on a statistics side and rather than the machine learning side, you might want to have a look at stats model, which is another project, which is another scikit. So you can use it with NumPy arrays and so on. And they have a bunch of linear parametric models with p-values and such. Okay. So back to the nonlinear models. So in Scikit-learn, we implement random forest and gradient boosted regression trees, or gradient boosted trees. Those are two kinds to build ensembles of trees that predict better than individual trees. So random forest, you build large trees independently of one another by introducing randomness everywhere. You compute the prediction and you average the predictions using a vote, or you can combine the probabilities and average them also. In this case, it's doing a vote, I think. And then the prediction of the random forest will have a lower variance than the predictions of the individual trees, so it should be better. There is another way to combine different trees, is to use a gradient boosting regression trees. Instead of having fully ground decision trees, we have first we train a very shallow tree, and we introspect the predictions how this small tree did errors, and we fit a second tree on the same data, but trying to predict the errors of the first model, and we do that sequentially. So the individual trees are very small, so they have a lot of bias, but few variance because they have a lot of bias. And by sequentially training them, you can counter this bias by giving the model more flexibility without introducing too much variance, because all the trees are very small. So those are two ways to build models, and they are very, very good at doing classification and regression. So you can train them as we did for logistic regression on exactly the same features. The only difference is the way that you construct the models and the hyperparameters. So in this case, for the random forest, we take 100 trees, for instance. And generally, for the random forest, the more trees you put in the ensemble, the better the prediction will be. But at some point, you reach a plateau, so it's not worth adding more trees, and it takes more time to fit. So you don't want to wait for ages to get your prediction. And here you can see that for random forest, you doing 5-fold cross-validation and computing the accuracy, you have 82% accuracy instead of 79 with the linear model. So it means that being able to model the non-linearity in the outcome is actually important on this data, because we have rather few features, and there might be some non-linear relationship between the features and the target value. With the gradient boosting classifier, you can see that we are reaching the same level of accuracy. It's comparable. The mean and max range are very much overlapping with one another. There is a couple of exercises. I will just do them quickly. So the first exercise is to change the value of the learning rate parameter of the gradient boosting regression trees and see the impact. And we can change the whether P class, we could explode it as a categorical variable and see if it has an impact on the model performance. And finally, which features are the most informative according to those models. So the first one is to actually change the learning rate here. So let's have a look. If I change it to decrease it, you can see that it's actually very sensitive. And if I increase it too much, it should be bad as well. Yeah, it's not that bad actually. Yeah, putting it more than one doesn't mean anything. So in this case, one is good, but most of the time, you need to decrease the importance of the sequentially trained trees to avoid overfitting. So, but we will discuss that later. So the learning rate parameter for gradient boosted classifiers is actually very sensitive. And it depends also on the number of estimators. So then we can explode the P class variable and treat it as a categorical variable, because there are 3 possible values, 1, 2, and 3. So to do that, we re-extract features. So we treat fur and age as numerical features. We keep them as such. And we extract dummies variables for those, and we remove the sex, the male. And we do the feature imputation, and we try again. So for logistic regression, we will reach the same level of accuracy as previously, so it doesn't really matter whether you treat it as a categorical variable or not. And for this guy, it's 82, and it was 82 previously, almost, yeah. So you can treat it as a numerical value or a categorical variable. It doesn't change much in terms of predictive accuracy. Finally, we can also introspect. Here we train a new gradient boosting classifier on the whole data set. So we fit it on features. We extract the column names as previously. And we do a bar plot, but this time, instead of plotting the coefficients, we plot this feature importances attribute. And it's an array of positive values for each possible features in the training set that summarize how much this feature was important for the trees in the ensemble. And you can see that the fur, the age, and the sex were very important. So it says that rich young female passengers were more likely to survive again. So it's compatible with the previous outcome that we've seen with the logistic regression. All right, so maybe we should do the break now because I think it's already quite late. And then we'll go on with parameter tuning. So 20 minutes break. All right. So shall we start again? Okay. So for the second part, we will finish with this notebook on automated parameter tuning, and then we'll see about how to do fine-grained model evaluation and diagnosis of the kind of errors model do. So here we are still with our data that we extracted, the features that we extracted from the CSV data using categorical variable expanding, using dummy variables. And then we are using nonlinear models, such as a gradient-boosted classifier. And we've seen previously that, for instance, the learning rate could have a very strong impact on the accuracy of the model. So it's very important to set this guy to a good value. So to do that automatically, we can do what we did manually by changing the value, running cross-validation, having a look at the mean score of the cross-validation, and doing that again for another value of the learning rate, and again, and record all the outcomes, all the scores, and finally pick up the best scoring value for the parameter, and use that to retrain the model on the complete data set at the end. So this is fine when you have only one hyperparameters to tune manually like this, but very quickly you will see models that have a bunch of hyperparameters, and they tend to interact with one another, which means that the optimal value of the learning rate, for instance, might depend on the number of estimators in your gradient-boosted regression classifier or regressor. And so you cannot tune them independently of one another. So to automatically tune them as a group, you can define a range of all the possible values that you want to try in a dictionary like params here, where you put the names of the parameter of the model that you are interested in. So to get the list of all the hyperparameters of a model, what you can do is create an instance with the default value and see the string representation. You have all the default values of the hyperparameters that are printed here. If you want to understand the meaning of those parameters, you can use you can use question mark in a IPython notebook, and it will display a window here with the docstring of the model of the Python class. And in the docstring, you have a generic description, some references in the literature sometimes, and the list of parameters. And for each parameters, you can see the type, the default value, the optional, whether or not it's optional. In Scikit-learn, all the hyperparameters are optional. They have a default value. And the meaning of the different parameters with respect to the algorithm that we are trying to fit. Sometimes you have recommendations on how to set them depending on the data, or some intuitions. But most of the time, you should be wary of intuitions, and it's better to do a cross-validation and trust the data rather than trusting your intuition. So here we decided to see if we could tune those parameters by fixing those two. So we fixed the number of trees in the ensemble and the subsampling that we do. It's random subsampling. And we will introspect the impact of the learning rate. We will introspect whether, when we are training the trees, whether we consider all the features at once, 100% of the features, or whether we compute, we find the best split to do a split in a tree on 50% of the features sampled randomly. Why would we do this? It's basically a way to inject additional randomness in the model, And sometimes when you are doing ensemble models, it might help. It might also help if you want to build ensembles of ensembles to have more randomized individual gradient boosted classifiers. Finally, we will also introspect the depth of the trees. So if you recall, for gradient boosted classifiers, we will train very small trees. We will constrain them to be 3 to 5 levels. Whether for random forest, usually you consider trees that are completely unfolded. You don't put any constraint on the depth. So by combining this parameter with this model, we combine them together by using this class, grid search CV, that takes the model as an argument and the list of possible parameter values, the dictionary of possible parameter values, and we give it a cross-validation strategy and the score that we want to optimize. And if we want to do parallel computation on a single machine, for instance, on this laptop I have four CPUs, I can use them in parallel to fit models in parallel and to score them in parallel, and then gather the best model. So this grid search CV is a class that is also an estimator. It's a meta estimator because it will wrap a base estimator, which is in this case is the gradient boosted classifier. It will wrap it into another scikit-learn object that also has a fit predict API. So we put the model and the list of parameters as hyperparameters of this meta estimator, and then we call fit on the data. So this will take some time. Shouldn't take more than a couple of seconds, 10 seconds or something. Yep. And then this model has been updated. So it has a bunch of attributes. So the first attribute is grid scores. I can display it, the attribute directly. Let me try change the resolution a bit. Sorry. Okay. The resolution is not good. I'll try to one more time. Okay. So it might be a bit too small. I will read the values that I want to highlight. So here, but you can reproduce this on your local machine to have a look at the values. So the attribute grid scores is a list of evaluation results. So for each possible combination of the parameters, we have a different row. So here, for instance, we pick up the first possible value of the learning rate, which is 0.05, the first possible value of the max features, and the first possible value of the depth. And we put them together, and we evaluate 5 models on 5 folds of the data, cross-validation, and we compute the mean scores of this combination of the parameters. And you can see that in this case, this first model, this first set of parameters, reaches between 96 and 97% of accuracy, and you have the standard deviation of the cross-validation score across the cross-validation folds. So here it's 0.03, so 3%. So it means that you shouldn't trust beyond the second digit, basically. So it's around 96 to 97% accuracy. So here the ordering of this list is the ordering of the evaluation, which is not very interesting. We might want to order the elements of this list by the mean score, the mean validation score, by using the sorted function of Python. So we sort the function, and we can see that those parameter values, max features equals 1, learning rate equals 0.5, and max depth equals 5, yields a very poor accuracy, 80%, whether this combination 0.5 for max features, learning rate 0.005, and max depth of 5 yields the best model with 97% accuracy. So you can see that apparently max features and max depth are not very impacting, because you can see that max depth of 5 is both there for the worst model and for the best models. The same is true for max features. It might be a bit biased to do subsampling, but the learning rate is very important, because when you have a high value of the learning rate here, all the models that have a high value of the learning rate, they have the worst predictive accuracy. And all the models that have lower values for the learning rate, they tend to be better. But you should take that with a grain of salt, because those scores are very close to one another. Most of them are between 85 and 87% of accuracy, and the standard deviation are overlapping. So you can see that even if you don't put the exact good value of those parameters, you still get the same predictive accuracy. So it's not very impacting. So let me grow back the resolution. The size of the fonts, okay. Firefox doesn't really like it. Okay. So this was the grid score attributes. You can also have a quick access to the best performing model by using best score and best params. And basically, the grid search CV object will automatically use the best parameters that it found during the search and retrain a new model using those parameters automatically on itself, basically. So this means that if you call gs.predict, you have a predict and a predict probability method, it will basically use the best model that it could find, retrained on the whole data set, and make predictions this way. So this is why it's a meta estimator, basically. You have a question?
So you said here the parameters don't seem to make huge difference.
Yes.
Do you ever risk overfitting onto the hyperparameters?
So the question is, in this case, the parameters do not seem to make a big difference. Do we risk to overfit the hyperparameters? And this is actually a good concern, because in this case you can see that the standard deviation are overlapping. So it might be the case that the best parameters here, if you consider the distribution of all the mean scores, it must be some kind of Gaussian. And if you order according to the scores, you will have some that are significantly better than the others, because they are on the different side of the Gaussian curve. And it might be the case that the best parameters that you find here are just by chance the best ones, but they are not significantly better than the others. So, and in this case, it will mean that we will overfit the hyperparameters. Usually, it's not a big problem to overfit the hyperparameters, unless you try many hyperparameters on a small data set. So if you have very small data, a small number of samples, you should be careful with doing grid search, or at least take it with a grain of salt. Another strategy to do hyperparameter tuning and to avoid overfitting is that some hyperparameters they are related to constraining the models or not. For instance, the regularizer of a logistic regression. When you take a large value, it means you regularize less. So if you see that two models have almost the same level of accuracy, but one has a stronger regularizer, you can pick this guy instead of the other, because it's less likely to be overfitting. So, for instance, the depth of a tree, if you take small trees, it's less likely to overfit. If you take a lower number of trees in a gradient-boosted regression model, it is less likely to overfit as well. So if you have a lot of overlapping parameter combinations this way, you can pick up the models that are the more biased to avoid hyperparameter overfitting, basically. So I think in the Element of Statistical Learning book, They say that whenever you have two models that are within one standard error, you pick up the model that is the simplest. So you could compute the standard errors and see what are the overlapping models and have rules to pick up the simplest models out of them. I didn't implement that. We should. So finally, for this data, we did the missing value imputation manually before doing the train test split. And this might be a problem because when we are computing the median values, we are using information from the test split, from the test fold. So it means that we are leaking stuff that should be hidden to us. So it might be the case that we have models that are scored better than they actually are because we are using information from the test set. So to avoid this kind of data snooping, what we can do is extract the data, and instead of doing the feature imputation with the median, we will replace the missing values with a marker which is numerical so that Scikit-learn doesn't complain, and do the imputation inside the cross-validation loops so that we don't cheat by using the data from the validation set, from the test set. So here we do the exact same pandas feature extraction, and we convert it into a NumPy arrays as previously, and we do the train test split as previously. But this time the missing values have been replaced with a marker which is -1, and an age of -1 doesn't mean anything, so it won't conflict with any possible value of the age. And so instead of doing the imputation manually in pandas, we will use this imputer class from Scikit-learn. And it has several strategies, for instance, imputing the median. And you can tell it that -1 values are to be considered missing values. And then it will record the median. Oops, sorry, I forgot to execute this. I have a deprecation warning. Should have executed that. This is weird. Sorry for that. Okay. So here my imputer object is an estimator. It has a fit method. So I pass it the training set only and not the full data set. And it will identify columns where there are missing values based on this attribute, and will compute the median of that column to later be able to do the imputation. So it stores the median values in the statistic arrays, and here the column number 1 is the age. So I can see the median age that it found. And in this case, it's the same, it's 28. But if you do several train test splits, it might actually be different. I think last time it was 29. Okay. Anyway, so it might have an impact by giving information from the test set. In this case, it's doing the same imputation. So now we can use the imputer object and call the transform method on the training data, and it will have the -1 values replaced by the median, and do the same on the test set. But this time we didn't use the test set at all to find the median, so we didn't cheat. So I do the imputation and I check that in the original data, this is weird. I should have. What did I do wrong? Okay, this is why. I didn't re-execute the feature, so okay. 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 So in the original data, I have some elements that have a -1 value. In the imputed data, I don't have any -1 anymore. So this is just a check. And this is the same for the test. Okay. So now that we have this imputer object, we can do the imputation manually by calling fit and then transform, but then it's tedious. Instead of doing that, we can combine it with the classifier into a compound object that we call a pipeline. So the pipeline, you can import it from the Scikit-learn pipeline package. You build the different stages of the pipeline, and you put them in a list as an argument to the pipeline class, and you put names for each individual stage. So we have an imp stage for the imputer and a CLF stage for the classifier. And then we can use that pipeline object as an estimator, as a classifier, and do cross-validation on the whole pipeline. So here I call cross-val score, but instead of passing the classifier, I pass the pipeline itself. So it means that for each train test split fold, it will compute how to do the imputation on the train part, and do the imputation both on the train and the test part, train the classifier on the imputed train part, and evaluate it on the imputed test part. So it will do all of that internally. So it's much nicer to do it this way. And you can see that in this case, we have, it's a bit lower, but I think it's not statistically significant. We have almost 82, between 81 and 82% accuracy. And this time we didn't cheat, because we are sure that we didn't leak any data from the validation set. So what is nice with the pipeline object is that we can also do a grid search of the hyperparameters of all the stages at once. So instead of doing a grid search only on max features and max depth, for instance, and the learning rate, on the gradient boosted classifier, I also try different strategies for the imputation method. And this time I will put my pipeline and the possible parameters into a grid search object, and it will use the pipeline instead of just the classifier. And if I do that and I sort the scores, okay, so again, we can see that the best models, they have imputation strategy of mean. You can see the bottom models have the best accuracy, and the top models have the worst accuracy. And this time you can see that all the mean model, they are on the bottom half, and the median are on the top half, which means that in this case, the actual imputation method is impacting on the accuracy of the classifier. And so it's significant that using the mean value instead of the median value for imputation is actually a better strategy for imputation. And we didn't cheat again, because we do it carefully. So yes, this is very nice with pipelines, that you can combine them with grid search and observe the interactions of the different stages. Pipelines, they can be useful for preprocessing the data, for instance, doing the extraction, the imputation. You can also do a PCA as a projection to remove a bit of the noise and to reduce the dimensionality. You can also do a standard scaling to remove the mean and divide by variance of each individual features to have them vary in the same ranges. You can also do, for instance, k-means clustering and then projecting to the k-means centers to find an alternative representation and extract new features this way. So it might be very interesting to combine supervised and unsupervised models into a bigger, more expressive model this way. And you can do the grid search of all the parameters using the same API as usually. Finally, a quick note. Whenever you're working with pandas data frames and scikit-learn, by default, because of the way pandas does the iteration over the elements, it might not fit well with the utilities of scikit-learn that expect slicing on the first dimensions. So there is, I think we will improve that over time, but in the meantime, if you want to use scikit-learn and pandas together and want to use pipelines of stuff that takes data frame as input, extract stuff, and combine them into a NumPy matrix inside the pipeline itself, you can use this project, which is called sklearn pandas, that provides you with additional utilities to make the two work together better. All right. Are there any other questions for this first notebook, which was quite long actually? Nope. Okay, so we can close it, shut it down, and open the model and selection and assessment notebook. Okay. So the goal of this section is to better analyze the kind of problems that we get with machine learning models, and in particular detect a problem which we call overfitting. Then we will see again hyperparameter tuning, but we will skip that quickly because we already addressed that previously. And then we will study the bias variance trade-off, which is linked to the overfitting problem, and see how to detect that and what kind of actions we can take to improve the model to take this analysis into account. So first we import NumPy and Matplotlib, and then we will use the digits dataset from Scikit-learn. So the digits dataset, if you were on there this morning, is just a bunch of pictures of 8x8 gray level pixels. So if you take 8 rows and 8 columns of pixels and you put them into a one-dimensional vector, that means that you have for each individual pixel a feature which is the brightness of the pixel, and so that makes 65 features, and we have more than 5,000 instances, samples, so individual digits drawn by students of this faculty, I don't know, this university. And so here you have the metadata of the dataset. So the digits data and the target variable, we usually store them into X and Y in Scikit-learn to have shorter variable names. And so the input data, they are the features, so the 64-dimensional features, pixel brightnesses. And then for each instance, we have the target value, and there are classes between 0 and 9, and the class integers values are the actual symbols that are encoded in the images. So we can have a look at the actual data by using Matplotlib. Matplotlib has this function called imshow, and you can reshape the data to 8x8 pixels and do this kind of interpolation to see the actual pixels. And we can plot them, and so we plot just the 5 first samples of a random permutation of the data. And you can see that the first image is a 9, and the true class in the label is a 9. And this is a 4, another 4, slightly different style, a 1 and a 5. Okay, so to get a feeling of the data set, we can do a randomized PCA in 2D to be able to plot and visualize the distribution of the digit from that original space. So randomized PCA is a faster version than the PCA from NumPy. It's approximate, but usually when you truncate the first components, they are very good. So if you do a scatter plot of the 2 first principal components of the data, you can see that the zeros are here. Here you have the ones, because they are very different from zeros, because the dark pixels for zeros are outside, and the dark pixels of ones, they are in the middle of the picture, so they are very well separated in terms of activation. And you have the same relationship between the 4 and the 3s, because it's right and left, dark pixels, and for 0 and 1s it's middle and on the edges. And so, and you can find the 2D distribution of the digits. So it makes sense, and it you can actually see from this that some digits are very easy to separate from the others, like the zeros, for instance. You can also plot the eigendigits. So by looking at the PCA components attribute, they have the same dimension as the original samples, so the same number of features. So you can plot them as you would plot features. And you can see that the first component, it's hard to tell, actually, in this case. So this, the zeros are at the bottom. No, actually, the first component is for this axis. So this should be closer to a 4 and far away from a 3. So actually, yeah, there is some correlation for this. I don't know. It should be dark here. I don't know. Okay, let's keep that. We can try to train the support vector machines on the digit dataset as we did this morning. And if we use the complete dataset to fit the model and then to evaluate it, you can see that we can reach 100% accuracy. And this is what we call overfitting, because it just means that the models was completely able to memorize the full training set. It can happen that some models, when you compute the score on the training set, have a training score that is below 100% accuracy, because the model has not enough capacity to to memorize everything. But for the support vector machines with the kernel, the RBF kernel, which is the default kernel, it's able to train the model perfectly, to memorize the dataset perfectly. So to know whether the model is able to generalize or not, we need to do the train test split as we've seen previously. And then compute the train score on the training side and compute the test score on the test fold. And here you can see that even if the model was able to perfectly memorize the training set, on new samples that weren't there in the training set, it just has 48% accuracy, or 49. Actually, it's not that bad because we have 10 classes, and they are balanced. So if you pick a class at random, you would have 10% accuracy. So the model is kind of generalizing a bit, but it's not very good. So if the test on the data, if the score on the test data is not as good as the score on the training test, if there is a big difference on the train score and on the test score, we say that the model is overfitting because it's memorizing too much the data without trying to generalize. If the train score is below 100% accuracy, if it's not capable of doing perfect prediction on the training set, it means that it's underfitting because it does not have enough freedom or enough expressive power to capture the richness of the original data. Sometimes underfitting a bit is okay because sometimes you have noise in your data and you don't want to perfectly memorize the noise. So there is a trade-off between the two. Ideally, if you have good labels without noise, you want to have the test score to be very close to the train score, and you want both of them to be close to 100% accuracy. You don't want underfitting and you don't want overfitting. In the previous example, we used the default hyperparameters for the SVC class. So you can see in particular that you have C equals 1, kernels equal RBF, and there is a gamma parameter which has a 0 value by default, which means that it's tuned automatically from the data. There is a bit of magic for this guy. We could fit a model with different values for those hyperparameters. So here again, if you display the model, you can see the values of the hyperparameters, and compute again the training score and the test score. And in this case, you can see that we can reach 100% of accuracy on the training score and 99% on the test score, on the test set. So it means that the support vector machines, they are basically able to solve almost perfectly this problem because the data is clean, the digits are well aligned, and it has enough capacity to both memorize completely the training set and to be able to generalize what it learned on the training set to the test set. So here again, we did a single cross-validation split, so we are not very confident in whether we got this good number just by chance or not. So if we do several iterations of cross-validation, we can use different cross-validation strategies. Until now, we used the k-fold cross-validation, where we split the data into equal chunks. Here, the shuffle split cross-validation strategy will do 3 iterations, and for each iteration, it will pick up at random 10% of the data and keep it as a test set, and keep the rest as the training set. So this shuffle split cross-validation strategy gives you more flexibility because you can do as many iterations as you want. And if you do that, you can iterate over this CV object, and it will give you a train and a test array, which are integers values that you can use to index your data to find the training samples and the testing samples. Using NumPy fancy indexing. So let me execute this so that you can get an ID. So here, the train array is an integer array. Here I display just the first 10 integers with the index of the samples that should be put in the train fold. And those are the indices of the samples that should be put in the test fold. So I do exactly that afterward. So here I put the part of X that is indexed by a train and the part of Y that is indexed by a train. I fit a model on this training set using those hyperparameters, and I compute the training score and the test score, and I report both using these print statements and some kind of Python formatting. And so you can see that on the first iteration, which is a random split, the train score is almost perfect, and the test score is slightly below, but good as well. And we get a bit of variability, but it's very good. It's very close to 1. So here I did it manually, but if you are just interested in the test score and you don't care about the train score, you can just use the cross-val score. Usually you are interested in the ability of the model to generalize. This is why we put the test score as in emphasis. So in that case, you can use the cross-val score exactly as we did before, but this time instead of passing a CV integer, we pass the CV object, which is the shuffle split strategy here. And you can see that the shuffle split strategy has some randomness, and you can fix the random seed as we did for the random forest by passing a random state argument again. So this is good if you want to have a reproducible outcomes. So here we do 10 iterations, and each time we hold out 10% of the data, but there are 10 random % of the data. And here you can see that the test score is very close to 1, but there is some variability. So to quantify this variability, you can compute the standard error of the mean. So you compute the mean of those 10, and if you want to have some kind of confidence interval, you can take plus or minus the standard error of the mean and display that, and you can be reasonably confident that the expected value of the test score of this model is 99% plus or minus something very small. Okay? Do you have any questions on this? So here is a small exercise to tweak a bit with the. Actually, we already did that in the previous stuff. So I'll move on a bit to see more new stuff. I will just execute them, and so we do the same, but this time we do many more iterations of shuffle split, of cross validation. with different values of the hyperparameters to have a test score that is a bit lower. It's around 90% accuracy. And here we use a bunch of stuff from SciPy to estimate the distribution of the test score. So we can plot a histogram of the test scores using matplotlib to see the variability. But a histogram sometimes is a bit too coarse. So you can use a Gaussian KDE, which is a kernel density estimator from SciPy, to kind of smooth the test score that you get to see the distribution, an approximation of the distribution of the test scores. And then you could take a confidence interval on this, for instance. Or you could use the bootstrap or something like this to get a better estimate. Anyway, so basically it's 90% accuracy on average here. If I change the value of this guy here, if I put 0.01, and I do it again, I can see that now I get a model that is not as good as well, and the spread is much bigger too. Okay. So we've already seen previously that you can do this procedure of cross-validation several times with different values of the hyperparameters. So here, in this case, I will try 10 values of the gamma hyperparameter of support vector machines. And for each value of gamma, I will do a cross-validation. So I will do 2 for-nested loops. One will iterate over the values, the possible values of gammas, and one will iterate over the possible train test splits. And I will record the train score and the train scores and the test scores for each possible of values of gamma and each possible cross-validations fold. When I do that, I'm then able to use matplotlib to plot the dependency between gamma and the training score and the test score. And this is for each individual run. I have a different line. So for each individual value of the train test split, I have one green line, which is the, I didn't put the legend, but green is the test and blue is the training score. And one blue line for the training score. So you can see it, so gamma is here, and here is the score. Blue means train, and green means test. So this is very interesting because it means that for some values of gamma, you have the train and test score that are very close to one another, and they are good, both of them at the same time. And so this is the regime that we want to target because we are really interested in maximizing the average test score, so this is very good here. But if we go on and grow gamma too much, you can see that the test score is going below, and while the train score stays high. In that case, we have a big gap between the two, and we say that we are overfitting because the model is perfectly able to memorize the training set, but is not able to generalize to new data. Whereas here, the model is underfitting because even on the training data, the model is not able to predict good prediction. So the intuition here is that gamma is the size of the areas that we will put around the samples. And so if you consider the samples independently of one another with a small kernel, you will be able to memorize perfectly the samples individually, but new samples that are a bit far away will be predicted at random because the model wasn't able to smooth the decision function over large regions. It will just focus on local elements. I don't know if there is a plot later. But we can also fix the value of C and see the impact. We fix the value of gamma and see the impact of C, and we do exactly the same plot as we did previously. But here we vary the range of C, so in the middle C equals 1, and this is 10 to the power minus 5 and 10,000 or 100,000 here. And you can see that for C, we have a different profile. We still have underfitting, where the training score is bad. But for this value of gamma and the different values of C that we try, we never overfit much. So depending on the parameters, we might have overfitting or not. Some parameters might introduce overfitting, and some other parameters might not. And sometimes the interactions between the two might trigger overfitting or not. So do you have any questions on this? No? Yes? So the default value for C is C equals 1. Yeah. It's L2 regularizer. So the loss is the hinge loss, and the regularizer is L2 for the SVC model. There is also a linear SVC model, which is a specific version for linear kernel models. And there you have more flexibility. You can change the loss, and you can change the regularizer between L1 or L2. And we also have SGD classifier, which is also a linear model where you have additional loss, many more losses, and more penalties like elastic net, for instance. But a different kind of optimizer, and that might have an impact on the performance as well. Okay, so all right. So here we see that the hyperparameters have a strong impact on whether the model is doing good at training and generalizing. And we can see that when we want to pick up the best value, we have an interactions between the two hyperparameters, C and gamma for support vector machines, for instance. So instead of doing that manually by doing those plots manually, what we do is we use the grid search object, and we try all the possible combinations, and we pick up the best as we did previously. So here it says the best value of C is 1, and the best value of gamma is 0, 0, 1. And on the test error is 97%. It's a bit lower than the score that we got previously, because here I did a random subsample of the data set to make this process run faster, because otherwise it's a bit too low. And as I have less training data on this small subset, the training score is a bit lower. So when you have expensive data expensive models that you want to grid search, it might be a good idea to start on a small subset, find good regions for the hyperparameters, and then focus on those hyperparameters and train on the bigger data sets, and iteratively refine the values of the parameters this way. It's less expensive. This function here is a way to compute the standard error of the mean of the individual scores, and to order the result of the grid search to have a better display. I think this should be by default in Scikit-learn, but it's not yet the case. And here you can see with the star marker here, the models that are either the best or within 1 star standard error of the mean of the best. So it means that all of those models, you cannot really say which one is the best. But those models, they are much worse. Actually, you can see 12% accuracy. It's almost random. But among those, you could pick up pretty much anyone. And actually, you can see that all the best performing models, they have gamma equals this value. So the value of gamma is very sensitive, whereas the value of the regularizer is not that important in this training set, in this data set. And this is actually what we've seen previously, because here you can see that the value of C, once you've picked up a good value of gamma, you can change it. It doesn't impact much the test score. But it's nice to have this all computed at once by the grid search object and not have to do it manually. Okay, so now that we have run the grid search, we can run it the grid search CV object automatically use the best parameters to refit an internal model on the training set, and you can use it to make prediction and compute the scores. And actually here you can see that we have 88% test value, whereas the cross-validation score was no, it was 98%, and the cross-validation is more like 96 to 97. And the test score is slightly higher because here we retrain the CV object, the GS object, with the whole training set instead of individual cross-validations folds, and the whole training set is slightly bigger than the individual cross-validation folds. So the test error is slightly better than what we evaluated with the cross-validation. Okay, so this is an exercise to do cross-validation and grid search on decision trees, but we did that previously, so there is not much interest in doing this. I will just run them. It's just that in Scikit-learn you can fit individual decision trees, and usually it's very bad. In this case, the decision trees have 80% accuracy, and you can try to limit the depth of the tree to avoid too much overfitting, but usually it's not very good at limiting the overfitting. So the best way in this case, we can check the overfitting of decision trees by computing the training score and the test score, and we can see that there is a gap. The train score is 100% accuracy, which means that the decision tree was able to remember the whole data set by heart, to memorize it, but it's not able to generalize very well. So when you limit the depth here we have no depth constraint. You can see that you can you can do slightly better on the test score, but you're no longer being able to memorize the full training set. So it's actually not a good way to reduce the variance, pruning the trees. It's not working really well. The best way to counter the effect of variance in decision trees is to do an ensemble of various decision trees. And so you can do that. And here you can see that the accuracy is much better when you do an ensemble. So here I use extra trees classifier instead of random forest. It's kind of a variant of random forest that is more randomized. So sometimes it's better, usually it's faster to train, but you need more trees, so there is a trade-off. Sometimes it's better, sometimes it's not compared to random forest. Okay. Well, I'll skip this and I'll focus on this, which is more interesting. So now we've seen that depending on the hyperparameters, you can have different overfitting or underfitting behaviors, and you have to know that the number of samples that you use in your training set might also have an impact on the capacity of the model to either underfit or overfit. So a good tool to study the impact of the number of samples on the quality of the training of the fitting of your model is to plot what we call the learning curves. So we will consider different subset of our training set with different sizes of the train sizes. So first we will fit a model with 100 samples, and we will grow logarithmically to 1,000 samples, which is almost the full data set, I think, in this case. So here, the log space utility of NumPy is very nice to this kind of scales, logarithmic scales. So for each size of the training set, we will record in an array the training score and the test score of a model. And we do a cross-validation. So we do a nested for loop. For each train size, we will do a cross-validation. So we iterate over the folds. And we train a model on the training part. And we score it both on the training part and on the testing part to have the train score and the test scores. And we record everything in those two arrays. So once we have those arrays, we can plot them, and we can plot error bars. So here you can see, so I fixed the hyperparameters of the model. I think in this case, I fixed SVCC equals 1 and gamma equals 0.0005. And here what I'm changing is the number of training samples. And again, I'm plotting the test score and the train score. So you can see that you have the same kind of relationship that we had with C, for instance. When we're increasing the training set, the difference, the gap between the train and test score is reducing. So at the beginning, with a small training set, you can see that we are overfitting by quite a bit. And at the end, the gap is less than 1% accuracy. Here it's almost, it's more than 10% accuracy. So you can see that having more data makes it possible for the model to not overfit with the fixed values of the hyperparameters. So this is actually a good way to counter overfitting. Whenever you observe overfitting in your data, is to try and collect additional data, additional samples, and label them. It might be expensive, but sometimes it's not expensive. It depends on the process you do for collecting the data. And actually plotting this curve and trying to do a regression or trying to do a prolongation of this curve on the right-hand side, you can see how much you would benefit in terms of increasing the testing score if you collected 1,000 additional samples, for instance. Here you can see that the slope here is far from being 0. So you can expect that you could increase by almost 1% accuracy by doubling the number of samples, for instance. So this is actually what I just said. So it's summarized here. So when the training set error is high, you have a high bias and your model is underfitting. Usually here, the training score is almost the same. I think we can't really see that it's moving. But sometimes it might be decreasing by quite a bit. The cause is that if your model is too constrained, when you add more data, it cannot memorize the additional data. And so it's forced to make some trade-off and forget about some samples or not being able to memorize them. So usually the train score is going a bit down, and the test score is reaching the train score at some point when you add new data. And when you have a few samples, usually you're overfitting by quite a bit, which means that your model has too much variance because you're not having enough data and the model is memorizing those specific cases by heart and not generalizing it. So the general strategies against overfitting is either to try and get rid of the noise in the features that you have, and maybe you have some features that are not contributing anything but noise. So you could try to ignore them. So in Scikit-learn, we have preprocessing steps that do exactly that try to identify the features that are not correlated in any significant way with the target variables to get rid of them before actually training classifier. So you could do a pipeline to do feature selection and then train the model. And by reducing the number of features, you can reduce the overfitting. You could also try to constrain the model by adding more regularization, for instance, by getting smaller value of C, by choosing a smaller value of C for support vector machines. Or for other linear models, we use the alpha parameter in Scikit-learn. For decision trees, you can use smaller decision trees. It introduces a bias that forces the decision tree to focus on the important stuff and ignore the noise. You could also try to switch to simpler model families. For instance, when you're training support vector machines with a Gaussian kernel, and you are overfitting too much and you don't know how to get rid of this overfitting, you can try a linear kernel support vector machine, and maybe it will be much better because it has additional constraints that better fit the data and get rid of the noise. So simpler model in Scikit-learn, you have linear models like linear support vector machine or logistic regression. You also have naive Bayes classifiers, the multinomial naive Bayes classifiers and the Bernoulli naive Bayes classifiers. They are very, very like linear models. So those guys, they are usually very fast to train, and on noisy data with a lot of overfitting, they might be better, actually. You can also build ensembles, like we did with random forest. So even if the individual trees are overfitting too much, by averaging the prediction of many random trees, you get a better prediction and you decrease the gap between the training score and the test score. And you can also try to collect more labeled samples so as to move your model in this region where the test score is better and reduce the overfitting, the gap between the two. So those are the general strategies. If you observe that your training score is not 100% accuracy and that it's big, you can try to address this underfitting by doing the opposite. So you have this trade-off between the two. So if you observe underfitting, you can try to give the model more freedom by decreasing the regularization or using deeper trees. You can also try more complex models instead of simple models, like nonlinear kernel SVMs or ensembles of decision trees. And you can also try to construct additional features. So, because if you are underfitting, it might be the case that your data, you don't have enough features to capture the stuff that you're interested in. So as we've seen previously in the first part, in the beginning we focused only on the numerical features, and then we constricted the categorical features, and it made it possible to increase the test score, and most likely by decreasing the overfitting. And because there is actual information in those new features that wasn't there in the previous ones. So if you're doing text classifications, for instance, using bag of words representation, there is a notebook on this later if you want to have a look. You can use barograms instead of individual tokens. So you combine two tokens and you make a new features out of them. You can also do feature cross products. If you have categorical variable like the class and the sex of the person, you could do the cross product of male people from the first class, male people from the second class, male people from the third class, as individual features using 0 and 1 as a Boolean indicator, and put that to your logistic regression model, for instance, and it might be able to capture new dependencies that are nonlinear because your new features are nonlinear, basically. Most of the time, doing cross-product of features with nonlinear models, like random forest, doesn't bring you much, but sometimes it does, so you might want to try. You can also do unsupervised feature extractions using, for instance, you train a clustering algorithm on your whole data set, and you extract many, many cluster centers, and then you project your data to those centers, for instance, by computing the cosine similarities. And you extract those similarities to the cluster centers as additional features, for instance. And it might help the model have a better representation that makes it easier to solve to better generalize to new data this way. Finally, you can also do other kind of nonlinear feature extraction using nonlinear kernel approximations. And we have some methods implemented in Scikit-learn. For instance, there is one which is called the Nystrom method, and there is another one which is called random Fourier features. Yeah, okay. So finally, we did the grid search on. Initially, we did a train test split, and we did a grid search on the train part. And we can do the final evaluation on the stuff that we didn't use at all during the whole model selection procedure. Actually, this is a good way to do it, because as we've seen previously, it might happen that if you have many possible hyperparameters and few samples, actually you would be overfitting the hyperparameters themselves rather than the individual parameters of the model. So the only way to check that you're not overfitting the hyperparameters is to keep a test set from the start and do the grid search on the development set and do a final evaluation on the test set and see if your test score is in line with the cross-validation score that you get on the development set. If you have a discrepancy, this is a strong hint that the model selection is actually overfitting because you don't have enough data, basically. And to do this development and final evaluation split, it's better if you collected the data over a different period of time to use a time-based split, because this is actually what is interesting in production. You want to build a model at some point, for instance, a spam classifier on the data from the past year, and use it on this year's data, on the current year. So if you use this kind of trend splits, you will be able to detect evolution of the distribution of the input that is time related. So there is a saying that says it's very hard to predict, especially the future, because of this, because there might be a shift in the distribution of the data over time, and if you don't this kind of temporal based split, you're not able to detect it. Okay, so finally, in this whole notebook, we didn't scale the data, and actually, if we had, we wouldn't have needed to change the default hyperparameters, because we scale data from for RBF model. It's much easier actually. So whenever you use a SVC model with RBF kernel, you should first scale the data, and it makes it much easier to get reasonable hyperparameter values. But even if you scale the data, you should always grid search. But so some models like support vector machines, they are very sensitive to data scaling. Other models like random forest, for instance, they don't care at all. So random forest is completely scale independent. So, but for support vector machines, it's important to do this kind of preprocessing, and you can use a pipeline to do so. All right. Do you have questions? Yes.
A note about sort of accuracy. A lot of this is kind of about accuracy. I would think that predicting who would die on the Titanic based on those variables, that you would expect there'd be things that you'd never be able to expect.
Yeah. Yeah.
It seems to me like it's just fitting that data just really, really well. But if I had the Titanic in another universe, that
Yeah.
It really wouldn't be that great.
Okay, so let me try to summarize this. But this is very true. So the remark is that also you should, rather than just doing cross-validation and modeling and this, you should think about what you are actually modeling. And in this case, in the first session, we were actually trying to predict whether a person will be able to survive the Titanic or not, based on the information on the class and so on. And if you find 99% of accuracy on this, with such few data, it's very suspicious, because the being able to survive the Titanic is such a complex process that depends on so many other stuff, whether you are sentimental, whether you have children somewhere else and you want to save them or something. This cannot be captured in the columns of the CSV file. So you will never be able to have enough features to make a perfect generalization. On the other end, for the digit data, you know that you have enough data in the features, because if you pull 10 people in the room and you ask them to label them, you will have an agreement that is very high, and if you make them vote, you have very good labels, and you are pretty sure that you can have perfect predictions, at least by humans. And so if the humans are able to do perfect predictions, it's very likely that if you are trying hard enough, you will be able at some point to make a machine that does the same. It's not always the case. Some problems are still unsolved, but it's a good clue. As if the humans are not able to do a perfect prediction, and you get a perfect prediction out of the classifier, it's very suspicious. So for the Titanic data, by just reading the CSV file, I wouldn't be 100% sure whether this person has survived or not. So it's a good grain of salt to keep in mind, to make sure that you're not doing something stupid, basically, by overfitting.
The goal doesn't have to be 100% accurate.
Yeah. Yeah. Also, the other remark is that 100% test accuracy is not always the final goal. Sometimes you have other constraints, and the value is being just able to make fast predictions that are good enough, rather than perfect predictions, but that takes one day to compute, for instance. For instance, if you are trying to predict the click-through rates for computational advertisement, you have 100 milliseconds to make your prediction, maximum. And actually, the machine learning algorithm just has 10 milliseconds. So you need to focus on small, fast models that take few memory. And so you have those constraints, and you cannot do 100% accuracy. So yeah, you have to quantify the business value and how it relates to the test score that you're measuring, be it accuracy or something, and find a relationship between the two and take that into account and take the other production constraint into account. All right, so we still have 7 minutes, and we won't have time to cover the next notebooks. But I can just give you a hint of what's in there. So the next notebook is an introduction to IPython.parallel, and basically it demonstrates how to do grid search and cross-validation in parallel, either on a single machine with multiple cores, or on a cluster, on Amazon EC2, for instance, or on a local cluster. So it might be very interesting when you are training on big data sets, actually not that big, but a couple of gigabytes of data and complex models like random forest. It might be very interesting to do hyperparameter selection and preprocessing and so on a cluster. And IPython.parallel makes it possible to do so. There are other alternatives. You might have heard of Hadoop. Hadoop is not very good for machine learning because it writes, it's too complex, but it might be very good for the feature extraction part. So because the raw data usually is very big, and the features that you extract, the numerical descriptors, might be much smaller. So a good pattern is to do the feature extraction in parallel on Hadoop, and then subsample it and aggregate the numerical features and do the modeling in a big workstation with a lot of memory. On a single machine, it's much easier. So this is a recurrent pattern that you observe. So you can use Python or R, for instance, for the machine learning part, and a Hadoop cluster for the feature extraction. But here we use just Python, and it's possible to use just Python if you don't want to mess with Hadoop. There is another notebook on text feature extraction, so if you're interested in classifying spam or sentiment analysis. And there is a refined version that takes memory constraints into account and deal with scalability of text feature extraction. So you can have a look at that too. Finally, I was asked to tell you about this. So you have 5 minutes to go to this URL and at least memorize it and at some point fill in the survey. Okay. So thank you very much. And I will be here around during the conference. So if you have machine learning questions, don't hesitate and to have a chat. Thank you very much.